Ladies and gentlemen, I am happy to welcome you to this year's TERINA Networking Conference, the TNC2007, which, as all of you who are here now have realized, is taking place at the Technical University of Denmark. In fact, we are in the Oticon building, a building donated by the Oticon Foundation. Oticon is a firm producing hearing aids. Only a few years ago, so this is a very modern building. We are on a campus where most of it dates from 1965, but we are in an institution which in fact dates back all the way to 1829. So we are in a place where old and new technology meets, where lots of sciences take place, and I hope that our conference here will be very fruitful, and there'll be a lot of exchange, both on the very advanced technical aspects of networking, and also on the many things that networks can be used for, because that's what's in the motto for this year's conference: visible services, transparent networks. The services should be really visible to the users and really useful. The networks should be really transparent. They should be there, they should work perfectly, which we hope, of course, they will do, also for you while you're here. And the goal, of course, should be to serve the scientific community and the students. Now, before I give the word to our two real speakers for this opening session, I have a few things to tell you. The conference, as most of you know, is organized by TERINA, the Trans-European Research and Education Networking Association. You see here our relatively new logo, just introduced half a year ago, and our new slogan, Networking the Networkers, which is exactly what we try to do, also very much at the annual TNC conference. It is hosted this year by UNIC, of which I have the pleasure to be the managing director. The Danish IT Center for Education and Research is our real name, but in daily life we call ourselves UNIC, with a large support, I should say, from the Technical University of Denmark and the National Research Network Forskningsnettet. Now we come to the housekeeping. Before we start on any talks here, please turn off the sound on your laptop and your mobile phone. We all know it can be really, really irritating if sounds go off in the middle of an important sentence. Also, there will be live stream. You are very welcome to try it out, but please not now. We know that many colleagues from the community who cannot be here with us physically will be trying to log in. So please wait a little bit before you start the live stream. Video archive, everything will be on video the next day, so you can watch today's presentations tomorrow and so on. And here is the URL for the place where the video archive will be available. Also, a warm word of thanks to all our many sponsors, most of all, of course, our main sponsor, Cisco, but also all the other ones: Jena, Juniper Global Crossing, Alcatel-Lucent, Global Sign, Extreme, Level 3, Google, Sun, Adva, Nortel, Force 10, Arkina, and once more DTU. And of course, we ourselves have also sponsored this a little bit, as is normal for the hosting organization. Now we come to the really important part of this opening plenary, the official welcome and the big opening speech. The official welcome will be given by Inge Mærkedal, who is the Director General for the Danish Agency for Science, Technology and Innovation. The agency is a very important part of the Danish ministry with the same name, the Ministry of Science, Technology and Innovation. And the agency is responsible for the research, innovation and secretarial services to independent research councils. The agency also, which is what makes Inge Mærkedal a very relevant speaker today, the place where the political guidelines for the Danish National Research Network, Forskningsnettet, are set, and I know that Inge will tell us something more about that. So, welcome to you, Inge, the word is yours.
Thank you very much, Dorte, and to the arrangers of this conference to giving the welcoming speech. Thank you very much for me. It's a great pleasure, mixed with a certain sense of pride, to extend the warm welcome to you all. Welcome to Denmark, welcome to Copenhagen, and not at least welcome to this conference. As the conference program shows, it must have taken really great effort and time planning to organize such a major international event. For this reason, I'm confident that everyone in this room agrees that there's every reason to extend our appreciation to the program committee, to the conference organization, to the sponsors, to the local host, and everyone else who have contributed to bringing this conference into reality. It also follows from the conference program that we are facing major challenges and a variety of possibilities. And in addition, there are a range of very technical and strategical questions to be involved. Questions that we have continually have to find an answer on in our effort to provide improved networks and services to scientists, to the educational system, to business and industry, to the man in the street and the society as a whole. I presume that you don't expect that I in any way are an expert in high capacity and high communication networks, grid infrastructures, interoperabilities, open standards, test beds, you name it. If someone should have had such an expectation, you will be very disappointed. However, as a user, as a government official, as a citizen, I am very concerned about and highly dependent upon efficient, fast networks that make it possible to distribute and make available scientific data, knowledge and technology, all around the world and between all kinds of institutions and companies. The Danish government is working hard to encourage as many users as possible to take up the opportunities offered by the new information and communication technology. And when I say users, it has to be understood in a wider sense of that word. Not only those students and researchers brought into focus today and the days ahead. Furthermore, the Danish government has pointed out that it is essential to make it easy, user-friendly, and safe for people to operate in a digital world. A well-functioning and competitive ICT market, a good framework for innovation, strengthened research, and more money well invested is a key to success for Denmark and other countries as well in the increasing and intense global competition. Nothing comes from nothing, at least only in the rare instance. For this reason, the Danish government has recently set aside fresh money for ICT research over a period of 2 years, the focus being on digital administration and pervasive computing. Moreover, I'm happy in mentioning it directly in the connection with this opening conference, the Danish government has quite newly decided to spend 40 million Danish kroner, which is approximately 5 million euros, on optical DMDW equipment and long-term lease of dark fibers in order to upgrade the Danish research network. My minister has asked me to write the check. It hasn't been done yet, but the decision is made and the money will arrive soon. These new money will, we believe, ensure communication facilities and services that will enable Denmark to match high international standards. The upgrade of the Danish research network is only the first step. This upgrade is a prerequisite for an efficient utilization of all modern research infrastructures. Having this basic e-infrastructure in place, we will be ready to carry through far-reaching investment in various research infrastructures during the next 3 years. Within 3 years from now, the government will spend a further 25 million euro on state-of-the-art research infrastructure that are of national strategic importance and that are, due to their large scale, generally utilized by several institutions jointly. At this moment, we don't know which type of research infrastructure projects will be materialized, since all projects are in direct and free competition with each other. Projects within all scientific areas are eligible for funding: neuron sources, research vessels, e-science, nanotechnology, biobanks, just to mention a few areas in focus. And to avoid any possible misunderstanding, these examples do not in any way mean that this specific infrastructure as mentioned has a finance guarantee. It's an open sense, so to speak. The decisions will be taken by the end of the year. We have recently received lots of proposals from the research institutions. They are now being internationally peer-reviewed, and the decisions will be taken by the ministry by the end of this year. Most, if not of all these new infrastructures to be established would have one thing in common, namely greater and greater demand on handling of data and information and communication technology systems. High capacity is a prerequisite for efficient and often decentralized utilization of advanced research facilities. Most of us present here today probably agree that science, innovation, and new thinking are decisive factors for improving today's knowledge society and maintaining our global competitiveness. In any case, I'm sure that each of you will fully agree that such policy goals cannot be achieved without the networks you deal with in your everyday life. At the same time, we have to realize how important it is to communicate this message in a committed, clear, and comprehensible manner. If we fail, it is not at all certain that we can maintain the interest and readiness of the politicians and taxpayers to invest in knowledge in the years to come. As far as I understand, the next speaker, Professor Catherine Richardson from Copenhagen University, will give an outstanding example how to communicate excellent research. A Danish research vessel has just completed a 257 days sailing around the world, a so-called Galatea 3 expedition. Hundreds of scientists have collected data and samples, and Danish pupils, students, and lots of others have been able to watch directly the daily work on board of the vessel, thanks to the transmission via the Danish research network. I can't help thinking what an astonishing development. I can't help making reference to Jules Verne's striking portrait of Phileas Fogg and his sky-high ambition in 72, to travel around the world for 80 days. The vision of Verne's were indeed far-reaching, even though he was not able to imagine the development of a communication structure enabling citizens of London at that time to currently watch the adventures of Phileas Fogg while he was traveling around the world. Allow me to bring my welcome speak to an end by pointing out two central issues, both having the classical adventure novel by Jules Verne as a starting point. Firstly, the costs. Phileas Fogg gambled everything to reach his goal. He was successful In the real world, governments have to recognize realities and spend public money in a little more responsible manner. In principle, we can never have too much processing power, speediness of our disposal. Yes, we have, but yet we have limits. We have to find the break-even level and can't always afford to say more of this and more of that and more is better. Innovative solutions in the future are at the stake of existing approaches prevent us from fresh thinking. Likewise, we have to avoid situations where we are forced to use outdated solutions and technology due to the previous and too heavy investments. The government is ready to make available the necessary money. However, big and fundamental steps are not always directly related to the amount of money, but often originates from the ability of thinking innovatively. Innovation often arises when you reach limits and not when you're giving lots of possibilities. This brings me to my second and last point. Keep up the good work. Let us be ambitious when we set our goals, and let us not forget to think right out of the box. Mr. Phyllis Fox, for 40 years an unworthy English gentleman who did everything in the same manner at the exact same time of the day, eating the same meals in the same club, playing the same cards, and every day reading the same newspapers in the same order. But at the end, he showed a remarkable creative ability, continually finding new means of transportation. This should also be the case for us today. I'm convinced that we will find completely new and cheaper ways of developing, storing, disseminating data and knowledge. Ways and means that are unimaginable today, and we need to think the unthinkable. Ladies and gentlemen, dear participants, with these words, I once again extend a warm welcome to you all. I hope that the Terina Network Conference 2007 will be stimulating and worth remembering for all of you. And I do hope that some of you, despite the heavy program, take some time to see part of the wonderful Copenhagen. Thank you very much for listening, and have a joyful conference.
Thank you very much, Inge, and I've heard that quite a few people were a little late for the beginning of the session, so if somebody wants to move forward now, there's room down here. Please. Up there at the door, nobody wants to come in? Yes, some people want to come in. I mean, there's plenty of room down here on the front seats. We are now moving on to the opening lecture, which will be given by Catherine Richardson, who is the Vice Dean of Public Outreach at the Faculty of Natural Sciences of the University of Copenhagen, and also a Professor of Biological Oceanography. Catherine actually has a bachelor's degree from Harvard University and a PhD from the University of Wales. Her research focuses on the conditions influencing the flow of carbon in pelagic marine foods, and is leading to the research project she's going to describe. She's also, I believe, going to tell us a little bit about the Galatea expedition, which was just mentioned briefly by Inge Merkedal, and how she uses the network in everyday research. So welcome, Catherine, the word is yours.
Thank you, Dawn. Does this work now? Yes, it does. I understand those people standing back there. They're all planning to make a quick getaway, but I'll do what I can to try and discourage you from making that getaway. I would dearly love to say to you that the fact that we've had 3 women in a row up here is typical of Danish research. Unfortunately, there are also statistical anomalies, and you've just run into one of them. Okay, it's been pointed out that I am a biological oceanographer. And no, I'm not going to try and tell you anything about how networks work and so on, but I want to talk about the interface between me and a network. And of course, I'm going to try and teach you something new as well, because I often find when I come to meetings, it's not when I go to the sessions where I think that the thing that's absolutely most relevant to what I'm doing, that's not where I learn something. I learn something by going to one of the other sessions that I really didn't think I needed to know anything about. And that's where the new things come in. So I'm hoping that a few of you will have an aha experience today with what I'm going to tell you about. Now, if I'm lucky, somebody's going to find my... Okay. Okay. I'm going to talk about global change in the ocean, and as you can see, all of these pictures here are actually taken from the famous Galathea expedition that Inge Markedale has just made famous for you. But I want to tell you a little bit about it because it really was something very, very exceptional that Denmark has carried out and has just finished. We came back here on the 25th of April, so we're still sort of reeling. Some of us haven't even gotten rid of our sea legs yet. What was this expedition? Well, it lasted for 8 months. We left on the 11th of August last year, and we came in on the 25th of April here. And you can see we started, there doesn't seem to be a pointer here, but we started in Copenhagen. We went over to the Faroe Islands, Greenland, down along the coast of Africa, over to Australia, around to the Solomon Islands. It says Honiara there. We didn't go to Honiara because of security problems there. We went to Gizo. And that's a very interesting story that I'm going to come back to. We went to Gizo, then to New Zealand, down around the Antarctic, up the west coast of South America, through the Panama Canal to Boston and back to Denmark. So it was a massive trip. Now, Denmark has a tradition of doing expeditions like this, and in fact there have been 2 other Galathea expeditions. One in 1845 to 1847 and one in 1950 to 1952. And you might say that, well, you know, hasn't time run out for this kind of an expedition? And yes, the answer is yes. If you think you're going to try and do an expedition like you did in 1840 or in 1950, which was natural history where we went out and we kind of, oh, look, see, there's a big fish. Yes, I mean, Jacques Cousteau's been there, BBC's been there, everybody's been there. So that's not what an expedition is about these days. And of course, in the 1840s, an expedition also had an economic end of it. I mean, let's try and sell some tea or find whatever. And we don't do that anymore either. So this was a very different kind of an expedition, but still a national expedition, not a research cruise per se, because, I mean, I've been on over 60 research cruises, and on a research cruise, you get the time that you've applied for on the ship. You, as the senior scientist, choose everybody that's going to be there. You know what equipment they're going to come with. You know what question they're going to ask because you brought them to ask that question. And in most cases, you also know the crew of the ship because you've been sailing on that ship for the last 20 years. So it's pretty routine. It's just, but this was entirely different because we applied, different research projects applied to come along, and the research councils looked at these and then and graded them, and the best projects got to come along. There were 71 projects in all, and we didn't even know the other scientists that we were out there with. And my own project was on all of the legs. A lot of projects were just on 1 or 2 legs, but I was fortunate enough that my project was along on the whole cruise. We don't have a research ship in Denmark that's large enough to take this many projects, and also the fact that we had 12 representatives from the media along on every leg, and students and teachers from the educational ministry and from various schools. So we don't have a ship that's large enough for that. So we used a naval ship, and we equipped it over a very short period of time. We equipped it into a modern research vessel, including all of the network which is required for dealing with this. I'll talk briefly about that in a moment, but I know there'll be a session in one of the, or a paper in one of the sessions this afternoon that goes into more detail about what actually was done on this ship. We were, of course, doing natural science research, and that's what my project is involved in. But there were also involved here, there were projects dealing with culture and history, mostly Danish history near the places where we were coming. And this is sort of really interesting because normally natural scientists don't work together with humanists or people from the social scientists. I told you on one of the earlier slides that we didn't go to Honiara because of security problems in Honiara, but in the Solomon Islands we went to Gizo. Gizo is a small island in the Solomon Islands, and here in the beginning of April, Gizo was hit by a tsunami. Gizo was very, very badly hit by a tsunami. You didn't read about it in the Danish newspapers because who knows where the Solomon Islands are? I mean, how many of you people know that Gizo was really, really wiped out by a tsunami in the beginning of April? But it was on CNN, and we on the ship, because we had such good access to net and so on, we followed all this in CNN. And one of the things that was really fantastic for us in visiting Gizo was the fact that most people don't know about Gizo, don't know about the Solomon Islands. And we realized that that very fact would make it very difficult for them to get help after this tsunami. So we said, couldn't we do something? I mean, we were there between the 29th of December till the 31st of December. Couldn't we do something? Couldn't we raise some money on this ship? We were 100 people on the ship, and I sat down and said, okay, if everybody gives 100 kroner, we'll have 10,000 kroner. That's, you know, something only on 1,000 to 2,000 euros. Well, I mean, you know, it's a help. I mean, yeah, let's do that. So we started doing this collection on the ship. But remember, we had media people on board as well. So the media people put it in the papers back home. So then there started coming in money from other places as well. So suddenly we had a rather large collection underway. And in the end, instead of getting 1,000 to 2,000 euros, we had 10,000 euros that we'd collected. And because we had contact to these land-based projects, who obviously weren't on the ship, these land-based projects found someone that could distribute our money, found a project, established a web page so that we can follow along on what our money's being used for, and found an NGO out there that would do all of the accounting for free. So in under 3 weeks from the time that Gizo was hit by a tsunami, we had raised 10,000 euros that were on the ground helping here. And that's thanks to the human network which was created here, but not least of which thanks to the electronic or the digital network that we had access to and able to do this. So that makes me think, you know, when I was asked to do this, you know, how much did we do because of our human network, and how much did we do because of our digital network, and how much was the interaction between the digital network and the human network? But I think it's worth thinking about. A few more facts about this expedition. The Crown Prince was the protector, is the protector. There were 100 people on board, where half of them were Navy people who were running the ship, and the rest were, as I say, media students and researchers. There was one change of the Navy crew, which means that they were out there for 4.5, 5 months each, where we scientists were lucky enough to come and go. I had 2 people on my project that were there for all 8.5 months. I myself went back and forth 3 times, one for a very short visit, but 2 longer visits, and in all I was there for 3 months. Public and private financing went into this, approximately $40 million US dollars. Interestingly enough, the cost the public cost of this exercise was about the same as what we pay for 1 year's subscription to be a part of CERN, which is the high energy particle physics in Switzerland. So this was a platform that we could work on, and a platform that gave marine researchers the ability to be able to study processes in different parts of the world. And as I say, there were 71 projects in all. Now, our data strategy, you could say, was really 4 arms. First of all, we had what we called Wind Collect on board, which is where from all of our instruments, data was sent to in serial format into Wind Collect. From there, it was sent to other instruments that needed to use it, or it was collected and we sent it periodically into land. And that meant that we had all of our technicians and so on, students, technicians, and all that working on land. There's really very, very little of, I mean, except for the data, except for my data where you have to have a microscope and look at a microscope and count how many cells of different kinds there are there. Basically, even though we came back on the 25th of April, everything is already worked up. Then we had a system up on the bridge which, where we registered all stations, when they started, when they stopped, what the weather was like, where we were at that particular time, and what instrument we were using. And it was the instrument that we had that chose or that selected how often the data was collected or recorded. Between stations, we also, of course, were running, collecting all sorts of data about where we were, and also we were collecting surface water characteristics and so on. And there we collected data every 5 minutes all the way around, although we could change that if we needed to, if we were in some kind of a situation where we wanted to have more frequent data collection. We had our profiling systems, and I've used those an awful lot. We had our CTD, which is conductivity, temperature, and depth, when we lower a sensor through the water to be able to measure what the water column really looks like. And these are interactive systems that we work on when they collect data. And I have to tell you that it was really very, very obvious much of the time that the people who had worked up these systems, made these systems for us, were at the time that they did it, I'm sure they thought they were exceedingly user-friendly, but they obviously weren't tired, seasick, and hanging on for dear life. It can be very difficult. I think this is one of the things we have to work on in terms of being users of systems, is understanding what conditions can be like in the field. I mean, for example, you can't really know when you start the station. You can guess and say, okay, I think the temperature is going to lie within this range and this range. But if you guess wrongly, you can't change the scaling underway. And if you're sending that instrument to 4,000 meters, it's a long straight line you got to look at without knowing what's going on down there. So there are a lot of, there's still a very great need, I think, for a close contact between the people developing and sending data systems and the people on the field, in the field. And then, of course, we had our ship information system, where we kept all of the data that we had already collected, and we could get it out in graphical terms, and we could download it into spreadsheets and so on, and actually work on it at sea there. As I said, we sent all this data to land. We had satellite communication the whole way. A tricky affair when you're in the Antarctic, I have to say, but we did have. And it worked much better than any of us had expected. We had certainly thought that this would not be the strongest end of the show here, but it worked very, very well. We had huge capacity from the ship. The reason we had huge capacity from the ship was partly because of the fact we had these 12 media people on board, so we also had live television from the ship. But we also did, I think I did 100 Skype conferences with classes. So we had basically conferences going on all the time. What was it that I was trying to do, or that we were trying to do out there? Well, basically, our project has a long, complicated name all about the carbon cycle, and Dorda kind of fell over it when she was trying to explain it, but let me try and make it a little more simple and a little more relevant to what we're all doing. And before I do that, or in order to do that, I'm going to start in an entirely different place, and I'm going to start out in space. Because a whole new science that I think is very relevant to people working on networks, but a whole new science developed about 15 years ago, or has been developing for about the last 15 years. And what happened is people went out into space and they looked back at the Earth and they said, oh my goodness, it does look like that might be a system that almost works together. I mean, you can see by the way those clouds are moving around, you can sort of imagine that there are things happening in the ocean underneath as well. And basically, what Earth system science states, or the general discoveries or the principles that have come out of Earth system science are that the Earth functions as a single system that's more than the sum of its components. It's not just land and water and air. It's land, water, air, and the interaction between land, water, and air. The other thing is that biology, okay, I'm going to talk about ocean biology, but biology, I mean, most of us, I look around the room here, there are a few younger people, but most of us, when we were in school, we learned that physics and chemistry decide what the world is like, and biology is sort of there as a passenger that comes along. That's not true. Biology is a really important player on the field here and is active in creating the system. There can be interactions in this system that have unexpected consequences. And finally, human activity is great enough to influence and change the function of this system. Now, when we say that, and I showed you the picture before of the Earth, and the other thing you can see when you look at that picture is not only that the different segments or the different components seem to work together, or that must be a system, it's also the fact 71% of the Earth's surface is covered by ocean. 71%. Now, when that is said, then you have to believe that the ocean must be very important in making that system function. And of course that's true, or I wouldn't be standing here today and I wouldn't have done all the work I did out on Galathea. But when that is true, why is it that every school child doesn't recognize that? I mean, after all, every school child knows that agriculture is bad, or farming is bad for the environment. But he also knows that that's why we have conservation areas and we have forests and we have... But they don't know anything about the ocean. And why is that? Well, the ocean, of course, is a foreign environment for us. We wouldn't survive very long if we were thrown out into the ocean. This picture I took on a cruise off of Iceland in the middle of winter. I think you would be conscious about 20 seconds in that water when you hit it. So it's a very foreign and hostile environment. Now that means that we're for the most part limited to standing at the edge of the ocean and looking out over it, which means that we don't get any idea of how big it is and how important it is. Or getting in a ship and looking down at it. But again, we don't have any feeling for what's really under us. Once, when we stopped once and had a swimming role on the ship, it was really jumping from the side of the ship, when you jump from the side of the ship, and that's 7 or 8 meters up, which I mean, I was really proud of myself for doing it. And when I told the captain how proud I was of myself, he said, oh, did you dive? No, I didn't dive, I jumped. And it was 7 meters, and that you knew you were going to go deep down into the water when you did that. The thing is, there were 5 kilometers of water under us. I mean, the feeling of jumping down and going down and knowing there's 5 kilometers of water. And I said that to someone. They said, oh, well, it's only the first 25 meters that count. And I'm sure that's right, but still, the thought of having 5 kilometers of water under us. A few people can come into the ocean for shorter periods of time in diving gear or in submarines or whatever. But even then, our senses aren't able to see what actually happens, to see the nature in the ocean and see what the ocean actually does for us. So the Galathea 3, in contrast to earlier expeditions where you went out and said, oh, look, there's a fish, many of the projects in this expedition focused on understanding how the ocean itself works. And as I say, many of the things that we looked at are very, very difficult to see because they're very, very small. Now, I want to talk about interactions between components of the system. Interactions between the air or the atmosphere and the ocean, for example. What do we know about the atmosphere? Well, we know that the concentration of CO2 in the atmosphere has changed dramatically over the last 450,000 years. This curve goes all the way back 450,000 years. Since these data came in 1999, this has been extended back to 650,000 years. Now, those of you who haven't run out the back door will recognize that it is very difficult. I mean, where do you get data for 450,000 years ago on what CO2 was like in the atmosphere? You do it by taking up an ice core from Antarctica. And you take that ice core up and you measure the air bubbles, you measure the gases. And here you have CO2 in blue and methane in red here. And you can see it goes down and up and down and up and down and up and down and up. But it always, until very recently, kept itself between 180 CO2, the blue line, between 180 and 280 parts per million. At the moment, oh dear, it's 2006, should be 2007. At the moment, we're at 375 parts per million. We know that because we measure it. And we predict that by 2100, it'll at least be 700, maybe even 1,000 parts per million. Now that's really very interesting because not only are we a place where we haven't been the last 650,000 years, but probably never, ever in the history of the Earth has that increase been as fast as it is today. We know as well that CO2 concentration in the atmosphere relates to temperature. Again, from these ice cores. The red line here is temperature. And now the ones, if there's anybody who's still awake, will say, ah, ha, 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 you can't measure temperature in an ice bubble. No, you can't. But you can measure oxygen isotope, the relationship of oxygen isotopes, which is a proxy for temperature. So you can get a picture of what temperature was like at the same time. And you can see there's a very fine relationship between CO2. When CO2 goes down, temperature goes down. CO2 goes up, temperature goes up. Why is that? Well, of course, you have the sun heats up the Earth. And if the Earth couldn't get rid of some of that heat, it would have burned up ages ago. And we know that it's hot in the day when you're outside, and during the night it gets cooler, and then this heat goes out. When this heat goes out into the atmosphere, gases like CO2 pick it up. Okay, we know we have this extra CO2 in the atmosphere. We know it's going to be increasing. So we try and predict, well, first of all, we look at what's happened to temperature over the last 1,000 years in the northern hemisphere. There's a lot of modeling going on down here that there's a lot of discussion about whether these are right or not, whether it's really whether we've gotten that part of it right. That's again done by proxies. I want to concentrate only on the last part here, which is by measurement. The end of this, where it's going up. Clearly, we are in a period where temperature is going up. And the International Panel on Climate Change predicts that by 2100, when CO2 concentration is at least 700 ppm, that the temperature increase on average will be between 1.5 and almost 6 degrees. That's average temperature. There is no animal or plant on Earth that lives at average temperature. You can have your feet in the oven and your head in the freezer, and you might have a fine average temperature, but you have problem with extremes. And that's, of course, what's going to happen here. And we believe in Greenland, for example, we can be looking at average temperature change of something like 12 degrees. But never mind. The point is that if it's 1.5 degrees, we can probably learn to live with it. If it's an average of almost 6 degrees, it's going to have huge consequences. So it's important to know why or how, whether we're talking about 1.5 or 6 degrees. Why can't we get it any closer? Why can't we get any closer than that? It's because we don't understand mostly because we don't understand what the ocean is doing in all this. You see here, the ocean has a contact. I told you the ocean covers 71% of the Earth's surface. And that means that in over 71% of the Earth's surface, the ocean is in contact with the atmosphere. Okay, so far so good. It comes in from the atmosphere into the ocean. Then you have some plants that can take it up. Most of that that's taken up by the plants gets respired out again. So it does come back into the atmosphere. You can say it's only on a short visit in the ocean. But some of it falls down to the bottom here, to deeper water, or even better, all the way down to the bottom here. Then it's locked away from the atmosphere. Then we've taken it out of the atmosphere, brought it down, and gotten it away from the atmosphere. If you look at the ocean, or if you look at the carbon cycle, the global carbon cycle, you can see that the atmosphere contains 750 gigatons of carbon. Believe me, when you add all of the carbon up that's here in the ocean, there's 50 times as much, 50 times more carbon in the ocean than the atmosphere. The atmosphere is in contact with the ocean over 71% of the Earth's surface. Tell me how you're going to predict what's going to happen to CO2 in the atmosphere without understanding what's happening to the CO2 in the ocean. You can see the ocean is still taking up more CO2 than it's giving off. It's taking up 92, giving off 90 gigatons. But the land, because of our fossil fuels and because of our deforestation, is now giving off much more CO2 than it's taking up. The ocean has, in fact, taken up about half of the extra CO2 that we humans have put into the atmosphere. That is to say, if we didn't have the ocean to have taken up this extra CO2, instead of looking at a concentration of 375 parts per million now, we would probably be looking at something like 460, 480 parts per million now. And we can even go in and say where this carbon is, and much of this carbon in the red area is in our area. Okay. These tiny plants that take it up, that make it so it could stay there, these are the tiny plants that live in the ocean. You can't even see them, but they're very, very different. They're much more different than the land plants that you look at because they're, evolutionarily speaking, much, much older, and that's important. But all of these plants have a very special job to do. They fix about 50 gigatons of carbon a year. They form the base of the food chain, and they contribute to elemental cycling. Now, I'll bet a lot of you are sort of proud of the fact that you think you belong to the species that's changed the environment most. You don't. You belong to the species that's changed it most quickly. But the prize for changing the environment the most, that must go to the blue-green algae, the cyanobacteria, that 3.5 billion years ago developed a form of photosynthesis with oxygen as a byproduct. Thanks to them, we have oxygen in the atmosphere so we can be here, but we have an ozone layer that protects us also from UV radiation. What's going to happen to these plants as the ocean gets warmer? Well, as the ocean gets warmer, you also get more rain. The ocean becomes more stable. You get a warm freshwater layer on the top, and you get a cold, saltier layer on the bottom. And as this difference becomes greater, it requires more energy to mix up bottom water to the surface water. Why would you want to do that? Well, all the nutrients fall down here, and all the light's up here. So if you didn't have mechanisms in the ocean to get this bottom water up to the surface, the ocean would be dead. But as you make it more stable because of climate change, it requires more energy to get the nutrients up. And it's predicted that there will be a decrease in overall plant productivity in the ocean, a decrease of about 10%. But that's on average. And again, it won't be evenly distributed. So we expect an increase in plant activity at the poles and a decrease in the middle. And what's interesting about that is that there are an awful lot of people on this planet that as their only form of protein have fish, and they live in the middle part there, the part that's going to have an even greater decrease in production. But I told you those plants were very different from each other. Some of them fix nitrogen, some of them make greenhouse gases themselves, some contribute to the Earth's silicon cycle, and some contribute to the world's chalk deposits. I want to talk just for a moment about those. Here's one. Here's the most obvious one, or the most numerous one. You can see it has these calcium carbonate plates or liths around it. And what happens is it can throw these liths off, and they're stone. I mean, they're made of calcium carbonate. They sink right down to the bottom. Or they can be eaten by animals here. And when they get eaten by them, obviously they can't digest those liths either. So they come out the other end, and when they come out the other end, they come with organic material. So now they have organic carbon on them as well, and they sink right down to the bottom. And you can see since we've gotten satellites, we can see where these blooms occur because those plates are actually like little mirrors that reflect light back. So you can see they're all over the place here in the ocean. And that means, of course, you have a lot of carbon sinking as calcium carbonate to the bottom of the ocean. And then you get the White Cliffs of Dover, or Møns Klint here in Denmark. This is all made by these tiny organisms that produce calcium carbonate, falls to the bottom, comes there, you have geological activity, and they come up again. So biology is an important player in the system. What happens? What happens when you get this kind of a picture like we have today? We've got more CO2 in the atmosphere. We've got the CO2 and the ocean, the atmosphere, in contact with each other. What happens? Well, the CO2 up here is trying to get into equilibrium with the CO2 down here. So you get more down here. What happens when you put CO2 into a water-based liquid? Why is cola bad for your teeth? It becomes acidic. And that's what's happening in the ocean. We can actually see changes in the pH in the ocean, where the upper line shows what the pH was like in 1750 when it was 280 parts per million for CO2. It's now fallen to about under 8.1, and we can predict where it will be if it goes all the way up to 700 or 750 in 2100. May not look like a large difference, but remember the pH scale is logarithmic, so it's actually a huge difference here. If we go back to our friend, the chalk flagella that we were talking about, Emiliani Huxley, Coccolithophora, the upper row there shows how they are when they're grown at the pH they live at today. The lower one shows what happens if you move them to the pH that we think will be there in 2100, and you can see that the liths are malformed. Now, it may not be that you can get your blood to really boil for these little guys. I think they're pretty neat, but I understand it if other people can't really get that excited about them. But you know other organisms that make calcium carbonate. It didn't do anything. Hello? Hello, hello? You know other organisms, and those organisms are corals. And you can see here, before we began to put extra CO2 into the atmosphere, that dark green area is the area where conditions were optimal for corals to be able to create calcium carbonate. The light green area is where it was adequate. And in the sort of yellow or the brown and red area, we don't expect to see corals. Now look at all those little black dots. That's where Mother Nature placed her corals. She wasn't as dumb as she looks. What does it look like today? Well, the dark green area has gotten much smaller, thanks to the fact that we have all this extra CO2 coming into the atmosphere. And the light green area, fortunately, most of the coral reefs are still in the light green areas. What will it look like in 2100? We don't have to go to 2100. By 2065, there will be no areas in the Earth's oceans at all where the conditions are optimal or even adequate for these organisms to produce calcium carbonate. And these aren't the only organisms that will be affected. This is the most important zooplankton group in the Ross Sea in the Antarctic in terms of transferring carbon up the food chain and also in terms of moving carbon to the bottom. And it's predicted, paper in Nature last year, it's predicted that they will disappear within the next 50 years. Now this story illustrates all those points that I was talking about. That interactions within the system can have unexpected consequences, that human activity does influence system behavior, and that global change is more than climate change. So what did we actually do on Galathea? Well, this was a global platform, as I said, and it gave us an absolutely unique opportunity to combine physics, chemistry, and biology to examine geographical differences in what's happening to the ocean and how ocean biology is changing because of this extra CO2 and also this exchange there is of CO2 between the atmosphere and the ocean. This, I think, is a really important point, the fact that we have biology, physics, and chemistry together, because we would never be able to do it without the without the digital possibilities that we have today with networks to be able to bring all this different data together. What did we actually do? I should also say we were from 4 different agencies or institutions. Here you can see a map of what carbon flux looks like in the ocean. This has never been done with biology, also looking at what happens, how much it gets caught when it gets into the ocean, how much of it stays there for a while. That's what we were actually doing. So we were looking at the phytoplankton, we were looking at remineralization, we're looking at zooplankton, we're looking at mesopelagic fish, and looking at how much of the carbon gets caught in them, and we're looking at the flux of carbon there. You can see that biology really does make a major difference. You can see this is some of our data from the Namibian coast. Here on the right-hand side, on the left-hand side, you have a satellite picture where you can see in the coast itself you have a huge bloom of phytoplankton. And you also have upwelling of cold water, which is high in CO2. And we see very, very high concentrations of CO2 in the ocean and atmosphere. Remember, I told you that the average concentration in the atmosphere now is 375 ppm. We're seeing measurements here of over 700. These are some of the highest concentrations ever measured. On our ship here, we were loaded with equipment. We have a strategy where we pump water in all the time that goes through the ferry box. So we pump water and collect data all the time on what's happening in the surface. We also have the possibility to stop the ship and to put sensors down, CTD sensors, where we measure a whole lot of different things. We also have the possibility to take undulating platforms after the ship to be able to measure what's happening there. We have a lot of different types of equipment, clearly all equipment that has to be linked together, where the data has to be linked together. Why did we do all this? Well, first of all, we want to try and be able to create a better database for improving models. We need to know whether it's going to be 1.5 or almost 6 degrees temperature rise. The other thing is we need to have a better understanding. We want to have a better understanding of how the system works. Why? Because with those concentrations of CO2 that you have in the atmosphere now, we're not going to solve the problem by turning down our emissions. We're going to have to seriously consider going in and trying to tweak the system, trying to get the system back to where it was before. The whole point is there's tons of carbon. There's 750 million gigatons of carbon in the ocean floor that was inert until we took it out, started burning it, made it active. We're going to have to start catching some of it and make it inert again. The ocean is one of the ways that we may be able to do that, but we have to understand how this system works in order to be able to not have unexpected consequences that are even more drastic than what we're doing. And a lot of people say to me, oh no, you can't mean that we should go out and play God and try and treat the system. We have inadvertently changed this system over the last 200 years. Is it more wrong to consciously try and change it back again than it was to accidentally make it get off course? So these are our two reasons for doing this. Our bottom line, I guess, is that nothing suggests that nature in the ocean is less worthy or less in need of protection than nature on land. We can't do this. We wouldn't be able to do this. We wouldn't be able to get this kind of an understanding for how such a huge system works if we didn't have the data and the network capability that there is today. It wasn't possible on the last Galathea expedition to try and do something like this. It is possible now. My final slide is that the ocean, or actually any ecosystem or the Earth system itself, is rather like a camel. They're very robust. They can take a lot of damage. When they break, you don't repair them by removing the last straw. This is the big argument, the big problem I have with people like Bjorn Lomborg that say, oh, well, climate change, let's wait 50 years, and if it's really a problem, then our children can decide they want to do something about it. But how are they going to get the corals back? It's expensive to repair them, and if they can be repaired, they will never be as good as new. So what we're trying to do, science-wise, now, as I say, would not be possible without the capability that you people have given us. And I think we're living in a very exciting, a challenging, but a very exciting time. Thank you for listening, and good luck on your conference. Are there any questions? No. Yes, there's one. Somebody that didn't run out the door.
You had mentioned stability in the. Is this on? Yeah. You had mentioned stability in the ocean with a freshwater layer as the temperature increases. what is your sense of, as temperature increases, the strength and frequency of storms and the role that those have in churning those layers?
That's something that people are, I don't know, I'm unsure which is actually working here. That's something that people are looking at a lot. I think probably in coastal regions that the storm activity will increase the mixing. Unfortunately, it's not really in coastal regions where you get this big deposition of carbon down to bottom layers. And it's also a lot of the deep regions in the tropics and subtropics that these poor people are dependent upon, you won't get increased mixing. But it's something, this trade-off between increased storm activity in coastal areas as opposed to what's happening out in the deeper waters is something that people are looking at a lot. And of course, there's also the very real probability that whole current systems will change because of the increase in freshwater influx, so that we won't have the North Atlantic current that brings the heat from the Gulf Stream up here. Almost all climate models suggest that there'll be a weakening. We will get less heat from the Gulf Stream up here, and those currents changing will also have consequences for food chains. Yeah?
In the press, there have been many more or less fanciful suggestions for washing out CO2 from the atmosphere, fixing it in the oceans or on the ocean bottom. You talked about tweaking the system. Do you believe more in using technology to do this, or tweaking the biological system? Or is it a combination of the two?
I honestly believe that there isn't one single solution, and a lot of people try and get me to say, oh, you know, this new thing the government has, you know, this isn't good enough, and, you know, Kyoto isn't good enough. You're right. None of these things are good enough alone. I think we have to talk about a basket with lots of eggs in it, and that one of the eggs is clearly more renewable energy and reducing our emissions. But others of these eggs include geotechnological fixes, and they can be either by tweaking the biology, for example, by trying to make the plants of the ocean take up more carbon. People talk about fertilizing parts of the ocean with iron and getting them to take up more carbon. There are others that are suggesting that we should go in and try and simply counteract the symptoms. There was a paper in Science earlier this year about putting off sulfur particles into the atmosphere that would, in the same way as a volcano cools the Earth, would be able to cool the Earth. So there are lots of different ideas out there. I don't think we have a good enough understanding of the system as a whole to use those ideas yet, which is why I think it's so critical to do this kind of work. But I do believe that it's really critical that, that we accept that those possibilities are out there, and that we have to take a culture, or our society has to take a decision on what it will do about it. I promise you, I know that there are Japanese and American firms that have taken out patents concerning fertilizing the ocean to get the ocean to take up more CO2. Why have they done that? Because they would be able to then, in Kyoto terms, be able to let more CO2 come out of their chimneys. And I don't, you know, if we're gonna do something as serious as treat the ocean, I don't think it should be to let some people put more out of their chimneys. So I think we need to be able to take societal decisions about this. But I have to say that it's problematic, because in our legal system, if you do something, if you act in good faith and you don't know that something could go wrong, then you can't be held accountable. But the greater understanding you have for a system, the more you realize things can go wrong, and we can start holding people accountable for any consequences that might come later on. So it's a really complicated social issue that we're dealing with here, but a really exciting one. We talk a lot about biotechnology, but I think geotechnology is on the same par and is coming soon.
You have told this Galatea expedition give very their new knowledge. But do you think this kind of expedition, this kind of data gathering should be done in the future on a frequent basis, or you think one's expedition per century is enough?
I don't think this is the kind of thing that can be done. I don't think it should be done too often. I mean, I think we as a scientific community in Denmark have gotten a lot out of this expedition because we've met people we didn't know were there. We formed these human networks that we didn't have before, you know, I think there's been a lot of value in it, and there's a very real possibility that the fact that we now work together with the Navy will be able to work where they are and so on. But no, I don't think an expedition is something you do every 5 years or every 10 years. But I'm proud of the fact that I live in a country that can do it every 50 years.
Okay, and the next question. There are, for example, network monitoring stations around the world, but I don't know about any permanent monitoring of deep oceans. Do you think it's necessary to make some permanent monitoring of deep oceans?
Oh, absolutely, absolutely. Because the thing is, until now, our society has looked at the ocean, and if you ask people on the street, I mean, what's the most important thing about nature in the ocean? What does nature in the ocean give me? They will say fish. And if you say to them, what are the most important organisms to protect in the ocean, they will say whales, and then they will say fish, and a few people might be able to get their blood to boil a little bit for starfish, but much lower down in it, you're not really going to get them with you. And in fact, it turns out that in terms of creating the environment that we have, the deep ocean and the smaller organisms are much, much more important, and people just don't recognize that, and they don't appreciate the nature in the ocean and how it works. For example, on land, when you look outside here, you see, the first you see of nature, that's plants. And those plants concentrate there where they get the most light. If the plants in the ocean did that, you would have a thick, oily scum at the surface of the ocean, which would prevent evaporation, which would prevent the rain on land. So nature in the ocean has entirely different ground rules that it operates on, and we don't respect them. The deep ocean is far more important to our environment here on land than those fish that everybody thinks is what we get from the ocean. So yes, absolutely, we have a desperate need for data from the deep ocean. And I have to tell you, it was kind of interesting that when we were out we were near the West Indies, and from our satellite pictures, from what we were working on, we saw ships dumping oil out there. So, and you could see what ship it was, where they were, at what time. It would have been peanuts to use that material to go after them. And we tried to interest the journalists on board to write about this because, you know, where is the legal jurisdiction? Who cares about this? Nobody was interested in writing about it. I mean, it's really amazing what happens in the deep open ocean. We have a desperate need to patrol it better and to monitor it. Okay.
Well, thank you very much, Catherine, for a very inspiring talk. And as you could hear, there were several interested questions, even though, of course, this audience is really here to discuss something quite different. But I think this was a good introduction to our conference. And this then actually closes our plenary session, our opening session. At 4 o'clock, there'll be 4 parallel sessions starting in building 303. So you have a choice. And I hope to see all of you this evening at the City Hall in central Copenhagen. I hope you can find your way because it's a remarkable building, and normally it's also a very good reception. So I hope to see you there, and thank you for coming to this opening. And once more, I hope you will feel feel welcome and happy here in Copenhagen, and I hope you will have a really enjoyable conference.